this computer. Okay, I think we're recording. Oh, and today we're starting chapter 22 already here. And this is, I know a lot of instructors actually skip this chapter because it's so abstract, but there are some results that can come from this relatively simply if you just accept the advanced mathematics, and those will be useful for some of the other things that we do, especially when we get to electric potential. So I'd like to work on that. And we're going to start with our first abstract concept, which is flux. And if, well, a decade or two ago, if I had talked about this, something that everybody would have seen was the Back to the Future movies and the flux capacitor that powered uh, Professor Brown, I think was his name. Anyway, his car or something like that. But now not so many people have seen that movie. But anyway, going to start with the idea of flux, and we're actually going to begin with the idea of just a stream. And let's imagine that we've got the banks of a stream here, and there's water in here, and it happens to all be flowing in this direction. And then we imagine that we have some sort of a rectangular loop here that's a flat plane of wire, and we'll just say that it has an area A, cross-sectional area A, and we'll imagine putting it into this stream so that we have water flowing through it. Now, if we put it into the stream so that it's oriented like that, we're not going to get any, well, we're going to get a maximum amount of water flowing through it in this case. And so we're kind of looking down on the area now, and we submerge it into the stream, and we'll get a maximum amount of water flow. If we orient it this way, we're not going to have any water going through it because the stream is going that way, and it's just going to be traveling parallel to the surface of that wire rectangle, and it's not going to go through there. Now, we're going to imagine drawing this thing. Here's our area A, and we're going to imagine that we have a surface normal to this area, and this is just a vector that is perpendicular to the surface in every direction, and the vector has a magnitude that is equal to the area of this thing. So the magnitude of the vector is not a length in this case, it's something equal to the area, but the direction of the vector is perpendicular to the vector. So this is perpendicular to area of loop. Okay, A happens to be. Okay, now let's suppose that we can just define a velocity vector for the water in this stream, and it's just parallel to the direction that the stream happens to be flowing. Well, if we have, if A and V are parallel, I hope that's how you, parallel. That looks about right, except I changed from printing to cursive there, but that's all right anyway. If they're parallel, we get maximum flow. Through A. And I'm going to write that A as a scalar. That's just through the area of the wire. If they're perpendicular, and B are perpendicular, we get zero flow. Through A. Okay, well, what about in between? Turns out the amount of flow through the thing will equal, and I'm going to use this for the flux of the stream through the area A. It's actually going to equal the magnitude of A, magnitude of the area, times the magnitude of the speed, times the cosine of the angle between A and V. And let me show you why that might be the case. If we've got V pointing that way and the A vector pointing in this direction, okay, remember A is actually perpendicular to the area A. This this is the angle phi between those two things. Let me show you what A cosine of phi is going to equal. Let's see. Oh, that's a little bit weird. Well, V cosine phi is going to be the component of the velocity that's straight through the area. I guess that's a way of thinking of it, except it's the area that we're playing around with. But as we rotate the area, that gives us V cosine phi. And that's the component of the velocity of the water that's actually going straight through the area. Another way of thinking of it is that A cosine phi has the effect of changing the area that's actually presented to the stream. And when we have it tilted, it's only a smaller area of the water or the square that's presented to the water. But anyway, phi is equal to the amount of water per second that's going to be going through there, which we're going to call the flux, is just going to equal that AV cosine phi. Well, A and V are vectors, and this is the magnitude of A, that's the magnitude of V, cosine of the angle between them, that's the dot product. So the flux of the stream through there is going to equal A dot V. And so the flux of the stream, if I multiply the area A times V, what I actually get is the number of, if the stream is measured in meters per second and the area is measured in square meters, what A dot V actually gives you in that case is the volume of water per second that's flowing through that area. And that's the way that you might measure a stream flow. They'd probably have something like cubic feet per second of water that's flowing through the stream. And they'd be interested, someone who's studying this, the stream flow would actually be interested in the total amount of water that that stream is carrying, but you'd measure it in the stream flux like that. They may not use that word, but that would be what they're interested in. So that's an analogy for water flowing in a stream. We are going to, well, you could define the flux of anything that you can define as a vector field. And maybe you won't use a V. You might use V is what the vector field is in this case. It's the velocity of the water that's going through there. But you could have an area in any kind of a vector field. And the vector field that we're going to be interested in is the electric field. So we're going to talk about the flux of an electric field. So for that, we'll use the same symbol there. I think that's a capital phi or something like that, but we might just stick a little subscript of E on it. And in that case, we'll have Remember, the dot product is commutative. You might talk about the electric field through an area, and that'll be the flux of that electric field. Eventually, we are going to get to where we'll talk about a tiny increment of flux, and that would be the electric field at a point on the surface of something, and we'll have an E dot dA. But for starters today, we're going to just deal with some static, large enough areas that we can get away with using something like this. So what about units of the electric flux? Well, for the electric field, we have E is newtons per coulomb. For area, we'll have meters squared, and so we'll have something like Newton meters squared per coulomb, and they're just weird combinations of units. And we won't usually be all that interested in the flux itself. We'll be more interested in what we can learn from the flux. And so we'll just move along on something like that. So for a starter example problem, let's suppose we have a point charge Q here, and we're going to imagine that point charge Q, or we're going to imagine a sphere of radius r, and so I'm going to that surrounds this thing. And I'm just drawing it as a two-dimensional circle, but imagine that it's a sphere of radius r, and we want to calculate the electric flux that is through that sphere. So flux of the electric field through the sphere. Well, to do that, we need to know and actually we'll kind of be doing this E dot dA sort of thing here, where we'll be integrating over the area of the sphere, but we need to know the electric field at distance r away from a point charge. Well, it so happens that is kq over r squared, or a lot of times in the textbook, they're rewriting k as 1 over, it's case of E, 1 over 4 pi epsilon naught q over r squared, something like that. But at any rate, that's what the electric field might or would be a distance r away from a point charge. Well, let's see, if I want to know the total flux, what I'll have to imagine doing is taking this entire sphere and turning it into a whole bunch of little tiny areas, each of which is a distance r away from that thing. And this would be a vector dA, which is pointing outward away from the point charge there, perpendicular to the surface of the sphere. And I'd want to know what's the electric flux through that little thing. And so I really want a little d phi sub E there. So d phi sub E is going to equal E, which happens to point in the same direction as dA, because the electric field due to a point charge there points radially away, as does dA from that point in the center. And so I could call it the vector E along r hat dotted with dA, which is also pointing along, dA is an area, which is also pointing in the r hat direction. And anytime you take the dot product between a unit vector and itself, you get the magnitude of the unit vector times the magnitude of the unit vector times the cosine of the angle between the unit vector and itself. That's the cosine of 0, and which is 1. And so r hat dot r hat is just 1 in this case. And so the flux of the electric field here is going to be EdA. Well, if I want to know the total flux over the entire surface of that sphere, the flux of E, I have to integrate E dA over the surface of the sphere. Okay, this is going pretty abstract here. And sometimes we draw a circle on this integral to indicate that it is a closed surface that we're calculating the flux over. Well, on the surface of the sphere, we will always be the same distance away from the charge Q. And so the electric field in magnitude, which is what we have here, is constant. It can come outside the integral. And so I've got E times the integral of dA over the surface of that sphere, which is the surface of a sphere, when I integrate that, is 4 pi r squared. So the flux is 4 pi r squared times E. Well, that wasn't too bad. Not bad for an integral. However, E is this. That's the magnitude of the electric field there. So I'll have 4 pi r squared times 1 over 4 pi epsilon naught times Q over r squared. And I've got a few things that drop out of this calculation. The 4 pi for one thing, the r squared for one thing. And I get Q over epsilon naught. That's interesting. The flux of the electric field through this sphere is independent of the radius of the sphere. And it just equals the charge that's inside that thing divided by epsilon naught. So that's actually pretty powerful. Now, here's the reason it's independent of the radius. The electric field strength gets weaker with the square of the distance. It's got a 1 over r squared. The area gets bigger by the exact same factor of r squared. And so they divide out. That's why you make the sphere twice as big in radius. Okay, it'll have, 4 times the surface area, but the electric field has 1/4 the strength when you double the distance away from the charge. And so it balances out nicely. So when you have that, the flux of the electric field through that sphere just is equal to Q over epsilon naught. Okay, you can do all sorts of weird things monkeying around with this. For instance, let's see. I used to have a gadget for drawing ellipses. I have no idea what happened to that template, but let's just imagine that we can do something here where okay, I can leave the charge that I've got here, Q, right here, and this was my original. It's half of my original sphere, and I can do something like that and just leave it there. And for my other imaginary sphere, I'm going to double the radius of it. And so the bottom half is going to be like that. And then I've got this plane here that lies at the center of that plane lies the charge that we've got there, Q. And if we wonder about the total flux through this new surface that we've got, that is a hemisphere here of radius r, a hemisphere down here of radius 2r, despite the way it looks scaled, and then a flat plane here. Okay, well, the electric field points radially away from that charge. Turns out there is no flux through this flat plane here. This would be a washer shape is what it is. There's no flux through that because the electric field everywhere along this plane is parallel to it. And the flux that's through something is going to be E dot A. The electric field is going to lie in this plane, and A is going to be perpendicular to the plane, and it'll be EA cosine of 90 degrees for everything in that plane. There's nothing added to the flux from the plane part, or the big washer shaped area here. But I've got a hemisphere here. What's going to be the flux through it? Well, I figured out that the flux through an entire sphere of radius r was q over epsilon naught. This is half of a sphere, and it's independent of the radius, remember. This is half of a sphere. It would be 1/2 of q over epsilon naught. That's the top half. And I'd also have the electric flux through the bottom half. Remember, that ended up equaling the same no matter what the radius of the sphere. That's also going to be 1/2 of q over epsilon naught. Didn't mean to write it that way. But when you add those two together, you just get the total electric field through this weird shaped area now is still q over epsilon naught. And whatever the flux of the electric field happens to mean, that's just all it's going to be. So let's try some of the problems that I actually printed off for today and see how those work. I probably won't get through the last one, but we can try to imagine these. So we have a flat sheet in the shape of a rectangle with sides of length 0.400 meters and 0.600 meters. And it's immersed as if we were dropping it into water, but it's just going to be placed in a uniform electric field of magnitude 75 newtons per coulomb that's directed at 20 degrees from the plane of the sheet. So here's the orientation that we have here. If I say here's the plane of the sheet, okay, and the electric field here is going to be in this direction, and it makes an angle of 20 degrees. Don't have a lot of significant figures on this one. And with the plane of the sheet, and we want to know what the flux of the electric field is through that thing. Well, I can actually calculate the area of this thing pretty easily. 0.400 meters. I don't know why I've got 3 sig figs on those, but I do. Oh, I'm going to cross that out and write 20.0 degrees because I've got 3 sig figs on everything except that angle. All right, so this would be 0.24. 0.240 meters squared is the area of that. See if you can do that in your head. And the A vector is going to point in this direction. Okay, this is E here. And the angle I care about is the angle between A and E. Well, looks to me like that one's going to be 70.0 degrees. So the flux of the electric field through this sheet, and it doesn't say what the sheet's made of or anything. Maybe it's a sheet of paper. So it will just equal A dot E, which in this case is the magnitude of A, magnitude of E, and the cosine of 70.0 degrees. So 0.240 meters squared times electric field strength was 75.0 newtons per coulomb, and then the cosine of 70.0 degrees. The actual number isn't particularly important. It was just figuring out this expression and drawing the geometry that let us figure that out. But 4 times 75 times. Okay, and I get something that I have absolutely no intuitive feel for, but it would be 6.16 Newton meters squared per coulomb. But that's just an example of the way you can solve this thing. And I don't expect you to have an intuitive feel for if this is a large amount of flux or a small amount of flux or anything. It's just how much it is in this particular situation. So this stuff is pretty abstract anyway. Now, this time we have a stronger electric field. Its E is 2 kilonewtons per coulomb, so it's 2,000 newtons per coulomb. And what is the flux of this field through a square of side 10 centimeters in a plane parallel to the YZ plane? Oh, we've got a vector here. Okay, so I'm going to draw, just don't usually do these, but draw a little three-dimensional coordinate system. And I don't know if you've done much with this in calculus or not, but we draw X that way, Y that way. Z would be perpendicular to the two of those things. And those are all perpendicular to each other. And our electric field in this case points in the positive I direction. So, or the positive X direction. So that's the direction of our electric field here, parallel to the X axis and presumably everywhere in space. And the flux of this field through a square of 10 centimeters in a plane parallel to the YZ plane. Well, if it's parallel to the YZ plane, we may as well stick it right there on the YZ axis, but we could imagine sliding it in this direction, but it's going to be, that means the area vector of this plane is going to be in the same direction as E. So that's something that we'll have here. So in that case, for part A at least, the flux of the electric field will equal just A dot E, which since they're parallel to each other, the magnitude of A, magnitude of E, cosine of 0 is 1, so it's just going to equal AE in this case. And that's all it's going to be. So A is going to be, we don't have a lot of sig figs on this either, like 1, 3 on that, but let's just round it to 1. We'll have 10 centimeters, by the way, is 0.10 meters. So 0.10 meters, and we square that, and we'll get 0.01 meters squared. And then multiply by the electric field strength, which is, I'm just going to write it as 2,000 newtons per coulomb. Since we only have one sig fig on those other things, I'll follow the rules this time. And I get 20. So 20 Newton meters squared per coulomb. So Whoopee. All right. Then it says, what is the flux through the same square if the normal to its plane makes a 30-degree angle with the x-axis? I think for this, I'm going to change my sketch. And so I'm going to have the z-axis pointing that way, the x-axis pointing this way, and I'll imagine that the y-axis is pointing up out of the page at me. So there's my y-axis. And we're orienting this thing, this plane, so that its normal makes a 30-degree angle with the x-axis. So here's the plane again. Here's the normal to the plane, which is the vector A. And there's a 30-degree angle between that normal and the x-axis. Well, I can almost, no, I can't, because it's the cosine of 30 that matters. If it was the sine of 30, I could do it in my head, but I can't. Anyway, in this case, the flux of the electric field will equal A dot E, and there's a 30-degree angle between A and E, so it'll be the magnitude of A, magnitude of E, cosine of 30 degrees. And so the AE we just calculated. So it's going to be 20 Newton meters squared per coulomb times the cosine of 30. So I can just take it's still in my calculator. Oh, that's great. My calculator told me 10 times the square root of 3, which looked to me to be about, yeah, this is pushing things significant figures wise, but it's about 17. And to one significant figure, we'd still have 20 Newton meters squared per coulomb, but we could fudge a little and say that it's that. Anyway, there's another problem. And this one wasn't too bad so far. We're not doing much with it. This is a problem that, man, one of my first job interviews, it was down at Eastern Oregon, actually, and I flew out from Minnesota, and I had 2 job interviews on the same trip. One was at Whitworth. It was a college in those days for a 1-year replacement position, and the other one was down at Eastern Oregon for a tenure track position. And down at Eastern Oregon, I don't know why, but they asked me to give a lecture on Gauss's law, introductory Gauss's law. And so this was one of the example problems that I did. And then afterwards, the instructor told me, I don't actually do Gauss's law in my class, but I was just curious what you'd do with it. So, so it goes. Anyway, the positive charge Q is at the center of a cube of side L. All right, so, well, let's draw a cube of side L here. Let's see what we get. Okay, that's a really lousy cube, but right in the center of this thing, we've got a point charge Q. A large number N of electric field lines are drawn from the point charge. Okay, we haven't done much with drawing electric field lines yet, but here's something that we might do. And electric field lines are just something that we draw to give us an idea of the direction of the electric field. So for a point charge, if this is a point charge plus Q, a way that we could draw these things are just a bunch of arrows pointing away from this thing. And this would give us an idea of the way that the electric field looks like this. And usually when we draw them, we draw a few more, but not many more. Anyway, we just kind of draw things that look like this, and they'd be symmetric in every direction from this thing, so we could just have them looking like that. So those are electric field lines, and that's what the electric field looks like for a point charge, positive charge. If it's a negative charge, we'd have the same thing, except instead of having field lines that were pointing away from that thing, whoops, already did it wrong. We'd have field lines that point in toward that thing. So, and then have one here, one there, one there, and one there. So that's the way they'd look for a negative charge. If we had a positive and a negative charge near each other, now I'm getting a little bit far afield, but if we had a minus Q here and a plus Q here, what we'd end up with for the electric field lines is something like this. I don't know what direction that one was headed originally, but whoops, that's the wrong direction. Anyway, we'd get a shape that looks like that, and out here it's even wider and stuff like that. But anyway, this is called a dipole electric field when you have equal and opposite charges separated by a distance d, and you get this particular shape of electric field. To actually calculate the electric field out here at points that are away from the thing, you can calculate it along any one of these lines because they're perpendicular to that. But at other places, there's actually an infinite series that lets you calculate it at very different points. And it's the infinite series is called the Legendre polynomials. And that's something that is beyond the scope of this course, so we're not going to do anything with that. Okay, now I've completely messed up the area that I had for my example here, but we just imagine that there's some number, capital N, of electric field lines drawn away from this thing, okay? And N is a whole big number, and try to imagine it as a three-dimensional exercise. How many of the lines pass through the surface of the cube? Well, since they all point away from it, all N of them are going to cross through the surface of the cube. And so that's just something that we have. B says how many pass through each face of the cube? Well, this is symmetric, so I'd expect that I'd have the same number going through each face, and a cube has 6 faces, and so the amount that passed through each face of the cube would be 1/6 n, or n divided by 6. What's the net outward flux of the electric field through the cubical surface? Well, this has to do with Gauss's law, which we actually haven't touched on yet, but turns out the flux of the electric field through this entire cube surface is still, this would be for part C, I guess. The flux of the electric field is still the amount of charge that's in there divided by epsilon naught. Epsilon naught is a constant that's buried in that case of E, by the way. And we haven't actually done anything with it yet, but that's okay. Turns out this is the amount of flux through a surface, a closed surface, no matter what the shape of the surface happens to be, and no matter where the charge is in relation to the surface. So that's something that you need the divergence theorem from multivariable calculus to prove that. And I think I mentioned in the notes for today, or in the introductory material that I just posted, which you probably haven't seen yet, that in order to prove this Gauss's law that we're soon going to be working with, you need the divergence theorem, which is something that you learn in multivariable calculus. But most of the math books that I look at, the calculus books where you're getting to that, don't even, or they might mention Gauss's law of electromagnetism somewhere, but they don't emphasize it very much. And a lot of them just completely ignore it. And when I took the multivariable calculus class as an undergraduate, the person who taught it had no interest in physics. He'd never taught multivariable calculus before, so he was kind of learning it as he went, and we stopped well short of the divergence theorem, which for most of us, that was the main reason that we wanted to take the course, was to have a good understanding of that. That was a big disappointment. Anyway, the reasoning for parts D and E ends up being similar. It's just kind of hand-wavy stuff. But let me show you Gauss's law, which has to do with the flux of the electric field through the surface. And it's this. We write it the integral, and this means the integral over a closed surface. And the integral is the integral of E dot dA over the entire surface is equal to Q, and sometimes you see an ENC as a subscript on that, and that means the charge enclosed by the surface divided by epsilon naught. And that's Gauss's law. Now, we did it for a sphere with a point charge at the center, but it turns out it doesn't matter what the shape is, where the charge is inside there, it's always going to equal Q enclosed over epsilon naught. So this is Gauss's law. And it's one of the 4 fundamental equations of electromagnetism. This is Gauss's law, and I'll put in parentheses here for electricity. There's also a Gauss's law for magnetism, which we don't usually bother to study in this class, but I'll go ahead and write it for magnetism. It happens to be, we use the letter B to denote a magnetic field. And for magnetism, we have the integral of B dot dA over a closed surface. It's even easier, is equal to 0. Whoa. So that's the one for magnetism. And there's a reason for that. Anyway, sometimes you see this, and I can't remember how your book happens to write it, but you'll see Gauss's law written this way for electricity. It's E dot n hat dA is equal to Q enclosed over epsilon naught. And all they've done is taken the dA vector and turn it into something dA n hat. And so where you had this little area dA here, and we'd been talking about a dA vector looking like that, they just split it apart. The magnitude of dA, the vector, happens to be dA, the area here, and n hat is just a unit vector pointing in the same direction as dA. And sometimes I write it this way just because the book that I learned it out of wrote it that way. And I can't remember if your book does it this way or that way, but it means exactly the same thing. And that is Gauss's law for electricity. So I think I'm going to stop there. And Thursday we'll deal with, or not Thursday, but Wednesday, we'll deal with some applications of Gauss's law. And turns out Gauss's law is useful for calculating the electric field of certain charge configurations. And it's a quick way to get the electric field in those few situations. And so we'll deal with that. And otherwise, that's about as much as we're going to do with Gauss's law. We're just not going to mess with it any more than that. Unless, well, I do have a kind of a dry lab I do on it, but I'm not sure that I'll even do that this year. So we'll stop there for today. You have any questions? Oh, will there be a homework review session for the homework? I could do that tomorrow for a bit. Yeah, for an hour or so before the lab, or I don't know, some amount of time before the lab. I could do that. Any other questions? Okay, I'll stop the recording here. And